Good afternoon, everyone, and welcome back. So today we have a very prominent speaker with us, Dr. Bhavna Singh. Dr. Bhavna Singh is a Joint Director at a Regional Office, Dehradun, under the Ministry of Environment, Forest and Climate Change, Government of India. Currently, she is serving on the editorial board of Journal of Industry Ecology for a special issue on life cycle sustainability assessment, and as a secretary for life cycle sustainability assessment section. Her expertise include environment system analysis, life cycle assessment, energy and transport system, climate change mitigation. I welcome you, ma'am. So she is going to give a talk on environmental penalties of power production.
Good afternoon, everyone. Am I audible?
Yes, ma'am.
Thank you very much for the kind introduction. I realized I should have updated my LinkedIn details. I have now I'm posted in the head office in New Delhi. I have started looking into sustainable consumption and production, which is very much related to environmental impact analysis aspects. So again, thank you very much. I will try to share my presentation. Could you please confirm if it's visible? Like,
yes, ma'am, it's visible.
Okay, good. Thanks again for inviting me for the talk. What I plan to talk about today is, of course, the environmental assessment of certain electricity generation technologies, but also more importantly about the method by which we could assess different technologies for power generation or any kind of technology or products, and find out which fares better, which are more environmental sustainable options to choose from. So that is based on my previous research and that I did before joining the ministry. And since joining the ministry, for last 2 years, I found a unique opportunity to actually try to mainstream that kind of thinking, the life cycle thinking, into policy decision making. So we are developing a policy which mainstreams this concept that before making any selecting any options, we look into life cycle perspective of the things. So that is a very interesting opportunity for me. So let's go. Let's see what today in this talk. So I have devised my presentation like a lecture here. So shall I continue, or is there kind of a disruption? Okay, I continue. So I have devised this as a kind of a lecture here. So I will try to give an introduction to the method that could be used to compare different technologies, products, and systems. And then we'll showcase that how or what kind of results do we get when we compare low carbon technology, here a carbon capture and storage technology for electricity generation, with their conventional counterparts. And also will give you a glimpse of how different kind of energy systems, including CCS, the solar, and so on, compares with the conventional fossil fuels. Just a kind of overview of the comparison and the way forward. So we know that sustainable human development implies that we meet our today's development needs while sustaining the ability of natural systems to provide for natural resources and ecosystem services for future generations to come. So it focuses on economic development and social development of current generation and environmental protection for future generations. So the sustainable development idea binds together concern for carrying capacity of natural systems with the social, political, and economical challenges faced by the humanity. So there is an emphasis on the present generation's responsibility, that we are responsible to regenerate and maintain and improve our planetary resources for use of future generations. In 2015, the UN General Assembly declared Sustainable Development Goals, which are a set of 17 goals, and address the global challenges including poverty, inequality, climate change, sustainable cities, environmental degradation, peace, and justice. Of these 17 Sustainable Development Goals, two goals, goal 7, which is affordable and clean energy, and goal 13, which is climate actions, are explicitly linked to energy systems and their environmental stressors in terms of GHG emissions from these systems. Energy has been central to economic development, and global energy use has risen sharply since the beginning of the 19th century. Total primary use worldwide has reached about over 14 billion tons of oil equivalent in 2019. The relentless growth in energy demand and the continued heavy reliance on fossil fuels have led to large increases in carbon dioxide emissions, despite major technology-driven improvements in energy efficiency and growth in adoption of renewable technologies. Between the middle of the 20th century and the second decade, like 2020, global energy-related CO2 emissions, that is emissions from the combustion of fossil fuels in transformation processes in power generations have increased steadily, except during the periods of major economic disruptions, including the COVID pandemic ongoing. So power generation, where coal use is increasingly concentrated, is the biggest emitter of CO2 worldwide, accounting for about 40% of total emissions. For the fuels and technologies used to meet the growth in energy demand over the last century have undergone considerable changes. So as we see in these illustrations, that the technologies have moved away from coal in general. For the most part, each technological innovation wave to say has brought forward energy technologies with lower carbon footprints than those that were before. The share of coal in energy supply declining in overall terms for most of the 20th century. However, since the inception of the 21st century, the share of coal in global energy supply mix has increased with economic boom in China. The share of traditional biomass, which was almost the use of almost the only source of energy in many parts of the world, has steadily declined due to availability of other kinds of fuels. A persistent trend has been the rising share of electricity in final energy use, initially in industries, in buildings, and more recently in transport sector. Electricity now accounts for about 1/5 of total final energy consumption worldwide. So here we see a projection of about of the global energy demand in 2070 in two kinds of scenarios. One is the policy scenario where the policies which have been declared already by the governments, it is assumed that they have been adopted with respect to energy and the environment are implemented, including the commitments which are made by different countries under the Paris Agreement. In the SDS, or which is Sustainable Development Scenario, it is assumed that the energy sector evolves fulfilling the SDGs goals, primarily the SDG 7, which is access to energy and the climate action, SDG 13, and the air pollution, which is SDG 3. And related to that, air pollution. So in these two scenarios, we see that there is about in the sustainable development scenario, the energy requirement in 2070 only increases modestly with about less than 5%, while when in the scenario where stated policies are implemented alone, the global energy demand increases over 36% in 2070. Also, in the sustainable development scenario, we see a dramatic rise in the use of clean energy sources, with fossil fuel use falling rapidly, renewables rising from 15% in 2019 to about 60% share in 2017. Now, this was about the energy systems imperative for sustainable development. Going further on to it, we know that all our anthropogenic processes required for our development and well-being depends on the natural environment, as we extract resources from the same and also emit our waste and emissions into the system again. So it is very closely interlinked. So our well-being is very closely interlinked with the physical environment. Now, we all agree with that to achieve sustainable development, it is very important that the Earth's natural resources be used judiciously and efficiently while we minimize any adverse environmental impact on environment. So there are various concepts that deal with using these resources efficiently and keeping the environment protected. And for example, resource efficiency, circular economy, life cycle management, life cycle thinking. And to dive into these concepts, there are different kinds of tools available to, for example, environment impact assessment, life cycle analysis, life cycle assessment, material flow analysis, input output, and so on, which deals with the we could say kind of environmental accounting. When we look into comparative assessment of products and technologies, we could come across that when we that an option which is giving us advantage over certain categories might have trade-off over others. For example, for wind power, we know that it has little or no GHG emissions. So it is a better option over fossil fuels, but there could be certain trade-offs related to material availability, related to biodiversity impacts on birds and so on. So there could be trade-offs among different kinds of products. So we need a consistent comparison among different options that are available to us, so that an informed decision for technology selection can be made. So with this idea, I would now introduce a method that you might also be aware of, which is life cycle assessment. So this is a technique to holistically and systematically evaluate environmental impacts associated with the life cycle of any product, processes, or system. So the life cycle term itself indicates that all stages throughout the product's life, for example, including resource extraction, manufacturing, distribution, use and repair, maintenance, and end-of-life disposal, is taken into account. So the idea of life cycle assessment is to account for all environmental impacts to avoid any problem shifting from one life stage to other, from one location to other, or from one environmental problem to other. Life cycle assessment can be used to compare environmental performance of technologies and products in order to be able to choose the least burdensome or the option which has least adverse environmental consequences. It can be used to identify trade-offs and problem shifting, if any. It can also be used to optimize the environmental performance of a single product or of a company. It can also be used to guide policy decisions in support of sustainable development. So here, the figure illustrates a systemic design for any life cycle assessment and shows that the inputs and outputs from all stages of the life cycle are quantified and evaluated into environmental impacts. The stack has 4 consecutive stages: goal and scope definition, inventory analysis, impact assessment, and interpretation. In the goal and scope definition stage, the purpose or intended application of this study is decided, usually in terms of functional unit. Functional unit is a quantitative measure of the function to be fulfilled by the product or the service. System boundaries describing which process to include into our assessment, a level of detail, and the kind of data that would be required are established. And the method is decided that would be applied for assessing these environmental impacts and the impact categories that would be evaluated. The second step is the life cycle inventory. Inventory analysis includes construction of flow model according to the system boundaries as decided in step 1, which is goal and scope definition, data collection for all inputs and outputs for the product system, and calculation of amount of resource use and pollutant emission of the system in relation to the functional unit. So this is the main data intensive step in any life cycle assessment. This is to illustrate a generic flow sheet of a system where different nodes, which are numbered here 1, 2, 3 to 7, represent specific interconnected processes of the system required to produce any functional unit of the product. The nodes 1 to 3 represent the direct processes which are required to generate the functional unit of the product. And the nodes or the processes from 5 to 7 are the indirect processes which are required to feed into our direct processes. So in the practical sense of applying LCA, it becomes quite a complex network to deal with. Very briefly, just to indicate that the basic block of all LCA calculations is a normalized requirement matrix, which is simply that what a process requires, what kind of input is required, and what kind of stresses it has. So to put that in a matrix and develop a normalized requirement matrix, simply using a Leontief inverse of this matrix, life cycle requirements of inputs are evaluated for the final demand, say Y, which is then combined with the stressor matrix to obtain total stressor output associated with any final demand of the functional unit. This is to showcase different kinds of LCA lifecycle inventory modeling methods available. These vary in level of details, a complexity, type of data that is available and hence used. Just I will touch upon the two, which is the process LCA. Here, the foreground or the direct processes are defined in the physical terms, for example, kilograms or kilometers, so on. While the indirect processes are taken from a background, which is also in the physical data terms, which is a database, which is a given database. And the last extreme to the right is the integrated hybrid LCA, which could be termed as the most complex. Here, the background comprises of both physical and economic. It is the most complete kind of inventory development process, and it also accounts for feedback from the foreground back to the background itself. So it is generally used in scenario assessments where, for example, where a complete power mix is evolved, how it will impact the whole background systems where the power is used in other sectors, for example, industries and so on. The third step is life cycle impact assessment. So far we have the life cycle inventory. For example, that means that the amount of emissions that would come out from any of my product or technology. Now the question is that what kind of impact would that mean? So this is accounted in step 3. This step aims to translate the information on emissions and resources from inventory analysis to more environmentally relevant information and impacts, for example, global warming, acidification, etc. So in the first step, that is a classification, the inventory parameters are sorted according to type of environmental impacts they contribute to. And then in characterization step, they are the relative contribution of these emissions to any impact. That is, for example, what is the contribution of CO2 to global warming potential? Contribution of methane to global warming potential are calculated. The steps of normalization and weighting in the normalization step, which is a step before weighting, the characterization results are calculated related to the actual magnitude of each impact in the region, and then applying some weighting factors to each impact category, a single score is developed. Usually normalization and weighting are optional steps in any standard LCA. Now, from the impact assessment, we can have a number of impact categories. Global warming, acidification, eutrophication, different types of toxicities, and so on. There are different kinds of methods based on environmental mechanisms to convert the emissions of natural resources or stressors into midpoint level indicators. And further on, there are methods that convert these midpoint indicators into endpoint. For example, what is the damage from global warming to the human health, to the ecosystem? So midpoint modeling is a comprehensive approach with relatively good level of certainty, while the endpoint modeling has more structured and informed weighting across categories in terms of common understandable indicators, making it useful to wide audiences and are more understandable to decision makers. There are different characterization methods available, for example, CML recipe and so on. Typically, these methods provide average characterization factors, which are representative of a temperate region. The level of spatial detail varies from different environmental, different regions, different ecoregions. So characterization factors from one region may not be applicable to other region. However, this is a very complex field. For comparison purposes, we could still go with the standard available methods. For some mechanisms, for example, global warming potential, which is a global mechanism, special detail is not necessary as the impact exists on a global level. For other impact categories, like for example, water use, eutrophication, which are very regional in its properties, it is meaningful to have specially differentiated characterization factors. This LC impact methods provides special differentiated characterization factors with different resolutions as per available data, varying for different ecoregions, countries, continental regions, and so on. So I just wanted to say that from the standard characterization factors, which represent specific areas, the research is progressing towards developing region-specific characterization factors, which could be more representative for that specific region. And the last step is the interpretation. In this stage, the findings of the inventory analysis and impact assessment are combined, consistent with the defined goal and scope in order to reach conclusions and make some recommendations about the selections and so on. And now, giving an introduction of this method, I would now present when this method is applied to compare different kind of carbon capture and storage technologies. As we know that carbon dioxide capture and storage technologies involve capturing carbon dioxide from industry and energy-related fossil burning sources, that is from point sources, large point sources, using some solvent or other process, transport of captured CO2 to some safe, secure storage location, or also in, for example, if in a system of utilization to produce products, and if in case of sequestration, to store it away from atmosphere for long term. Fossil fuel fire power plants are the single largest point sources of CO2 emissions and form the most likely application of carbon capture and storage. CCS also draws additional attention as it allows continuing the use of fossil fuels required to satisfy the increasing energy demand. International Energy Agency has estimated that in a 2-degree scenario, fossil fuels with CCS will provide 13% of the total electricity mix in 2050. So it will have a significant share in the electricity mix. Also, in the same scenario, CCS will provide sizable CO2 emission reductions in power sector, industry, and fuel transformation, and amounting to a cumulative CO2 reduction in power sector amounting to about 50 gigatons. So giving a generic overview of types of options that are available to us in this technology. So carbon capture technology comprises of 3 components, as we know: separation of CO2 from any large point source, from industry and energy-related sources, transport to storage location, and long-term sequestration away from atmosphere. Now, in the capture, the post-combustion capture systems separates carbon dioxide from flue gases generated from large-scale fossil fuel combustion, such as power plants, cement kilns, and industrial furnaces. Absorption process based on chemical solvents is currently the preferred technique for post-combustion capture. Pre-combustion capture system principally involves producing a mixture of syngas from primary fuel and then separating the carbon dioxide stream. The hydrogen stream so produced is then used the fuel. In the oxy-fuel combustion capture systems, this involves burning fuel in a nearly pure oxygen, producing a nitrogen-free flue gas with water vapor and carbon dioxide as its main components, and water vapors are condensed, so creating almost a pure carbon dioxide stream. Coming on to the transport options, pipelines are the most established and common method for transporting CO2. Gaseous CO2 is dried and compressed to pressure above 8 megapascals in order to avoid the two-phase flow and increase the density, making it easier and less costly to transport. Pipelines can be designed for onshore and offshore CO2 transport. Geological storage of carbon dioxide can be made to oil and gas reservoirs, deep saline formations, coal beds, and use the same technologies as developed by oil and gas industry. Prior to its storage, carbon dioxide is compressed to dense supercritical fluid state and then injected into rock formation at estimated secure depth. Other options, for example, ocean storage could be done by injecting CO2 into water column at the sea floor depth, and it then dissolves and dispersed, eventually becoming part of the global carbon cycle. Mineral carbonation involves converting carbon dioxide to solid inorganic carbonates, which are stable. So there is a set of options available. This figure is just to illustrate that there are a wide range of technology options for CO2 capture, which are in various stages of development, availability, and economic feasibility. So various factors are to be considered for deciding the role of CCS in climate change mitigation, including cost and capacity of emission reductions, demand for primary energy, and range of applicability and associated technical risks. Other important factors are the social and environmental consequences, the safety of the technology, the security of storage, and ease of monitoring and verification of the site. Now, giving you briefly what the technology is and what the kinds of options available generically for this technology. I will showcase a comparison of a select set of CCS options compared to the conventional options. Now, why do we need to compare? Why can't we just select one technology which is available to us as of now and go ahead with it? Is because the CO2 capture technology has certain issues with it. For example, the capture process itself is energy intensive. So it creates a kind of energy penalty on the power plant. This results in consumption of more primary fuel to produce the same amount of electricity, increasing the emission of non-CO2 pollutants from combustion and other fuel production-related emissions. Further, there could be solvent-related emissions and waste generated from degradation by products. Capture facility and extensive infrastructure needed to be developed for capture plant and transport and storage facilities. Thus, the CCS induces a demand on fuel, chemicals, and infrastructure, increasing the indirect emissions in the value chain and direct emissions from power plant and capture facility. So application of CCS technology on large scale may result in huge magnitude of such emission. Therefore, a trade-off in environmental impacts is expected, and therefore a systematic process of evaluation for all stages of CCS and impacts related to large-scale CCS deployment is needed. I will showcase comparison of 3 CCS systems for coal and natural gas each. So post-combustion, pre-combustion, and oxy-fuel, both for coal and natural gas. So how they compare, and for comparison, these technologies are compared to respective counterparts. A functional unit. So the comparison is drawn for 1 kilowatt-hour of the electricity. Just to showcase, just to illustrate different types of system in the post-combustion capture process, the treated flue gas is passed through a chemical absorption column where the solvent takes up the carbon dioxide. The carbon dioxide rich solvent is regenerated by heating in this stripper unit, and the carbon dioxide is then compressed and supplied to the pipeline. In the pre-combustion capture process, steam and oxygen are added to the primary fuel, producing syngas, which followed by the shift reaction to convert to carbon dioxide by addition of steam. The carbon dioxide is removed and the gas mixture then supplied to the combined cycle power plant. This mixture with about 15 to 60% concentration of carbon dioxide and a total pressure of 2 to 7 megapascal is then sent to separation stage where carbon dioxide is captured using, for example, a physical solvent. In this system, it is a Selexol-based physical solvent, and then the post-combustion, it is a monoethanol solvent. In the oxo-fuel combustion process, fuel is combusted in pure oxygen, and thus eliminating nitrogen from the flue gas. And the flue gas consists mainly of carbon dioxide and water vapor, which after cooling contains about 80 to 98% of carbon dioxide. The captured carbon dioxide is supplied to the transport chain at 110 bar and transported. It is assumed to be transported over 500 kilometers to a geological storage site. Transport mainly requires construction, maintenance, dismantling, and monitoring of the pipeline. Some additional energy would be required to recompress CO2 due to the pressure drop. The storage mainly requires drilling of the well, CO2 injection, and monitoring. Carbon dioxide is to be stored above supercritical pressure, therefore additional energy is required prior to injecting. It is for the comparison purpose in the system, it is assumed that the CO2 is to be stored at a depth of about 1,000 meters below the seafloor. Even prior to drawing the comparative LCA, we found that some information were then not available. For example, what would be the impact on human toxicity human toxicity of the solvent? Because at the time it was under discussion that the solvent itself would be toxic. So it was very much under debate to go to use it or not. So the work started with coming up with the understanding of the human toxicity related to the solvent. In an ideal monethanol amine and carbon dioxide absorption system in the post-combustion, the solvent is continuously recycled and reused. However, in reality, as the solvent has a relatively high vapor pressure, which results in significant vaporization and solvent loss. Additionally, the solvent MEA degrades and is known to react with flue gas impurities as SO2 and NOx. Solvent degradation is a major concern. Firstly, as it results in loss of CO2 scrubbing capacity, and fresh solvent must be continuously added to the process. Secondly, there is formation of degradation products, which affects the functioning of the equipment, and these degradation products may result in increased environmental impacts. So first, the human toxicity characterization factor for the solvent was calculated. Now for the different systems that I have outlined previously, the table shows the performance parameters, giving out the efficiency, energy penalty from each capture process, the amount of solvent required per ton of CO2 captured, the emissions related to each direct emissions from each kind of system. So this is to reflect different performance parameters which are used to model the life cycle inventory of these systems. For the comparison, a tiered hybrid model is used to model the system. That means that a background with physical data sets and a background with economic data sets are combined together to and used collectively to make it a more detailed system. A detailed unit process level information is used in the foreground, and then available recipe method, which now there are improved versions of this method itself available, has been used for characterizations of the impact. So now to the findings. Firstly, we know that carbon capture is a technology targeting CO2 to extract CO2 from the direct emissions of the flue gas. So we find that in the case of natural gas combined cycle power plant, without CO2 capture, the life cycle emissions are about 425 grams CO2 per kilowatt hour. No. And about 86% or over 80% of these CO2 emissions are from the direct emissions from the power plant. And the rest are from the natural gas production and infrastructure development. Now, in a case with the with CCS system in place, the emission intensity of the system reduced to 125 grams CO2 per kilowatt hour. The capture process at the power plant facility captures 90% CO2 from the flue gas. So this was specified in the tech performance parameters that I didn't go into detail, but the capture process has the capacity of 90% CO2 capture. However, additional carbon dioxide is generated from fuel combustion because of energy penalty, as well as operational inputs and infrastructure required for capture, transport, and storage. The increased carbon dioxide production results in a larger amount of CO2 generated per unit of products. So with the system, with CCS, we generate more CO2 at the first place while capturing at a targeted process. So with CCS, instead of 425 grams CO2, first we generate 508 grams of CO2. Total CO2 captured in production of electricity with CCS is about 90% of the direct emission, and is about 383. And thus, the capture efficiency of 90% in fact results into CO2 captured efficiency of 75% when we look into the whole life cycle. Even more relevant term to understand the net benefit of CCS is the amount of CO2 avoided. This value reflects the amount of CO2 prevented from being emitted by putting CCS system in place, and is calculated by comparing the CO2 emissions caused from the production of same amount of useful product as a reference plant without CCS. Is this found that with 90% CO2 capture efficiency, the CO2 avoided is about 70%. So just to give understanding that the process targeted the CO2 capture at the specific process, how it reflects upon the whole life cycle. Now, this illustrates how different environmental impacts compares with and without the CCS for a natural gas system. So in addition to carbon dioxide emissions, there are various other direct and indirect emissions throughout all the processes, from raw material extraction for fuel, infrastructure, and other materials required to waste treatment and disposal. So we see that the global warming shows a significant reduction of 64% in terms of CO2 equivalent. 64% here is in terms of equivalent, while previously we were talking only about the carbon dioxide accounting. CCS variant has significantly higher toxic impacts with increase of about 120 to 170%. So there is a concern. The main contribution to human toxicity is generally associated with the infrastructure requirements and heavy metal emissions associated with the material production. The assumed emission of MEA, formaldehyde, and acetaldehyde, which are the degradation products of the solvent, results in net increase of about 30% in direct human toxicity impact. Direct emission of solvent vapor, MEA vapor, from the absorber contributes only about 0.2% of the total toxicity from the complete life cycle. So sorry. So overall, it is found that the reduction of global warming potential has considerable trade-offs. The direct emission of solvent, formaldehyde, ammonia, acetaldehyde contributes significantly to acidification and various toxicity potentials. This is to illustrate a structure path analysis to elaborate structure path analysis of global warming potential to elaborate the net CO2 equivalent from various value chains for both the cases. So global warming potential due to direct emission from electricity generation is given in tier 1, and global warming potentials from induced background processes is given in tier 2 and 3. Net reduction of 64% in CO2 equivalent is substantially lower than the total reduction of 70% due to the emission of greenhouse gases substances throughout the value chains of the systems. The contribution from transport and storage chain is relatively small at only about 3% of the global warming potential impact. This illustrates the six systems or six CCS systems as compared to their respective one without CCS systems. So it is seen that even without CCS, there is a huge potential of controlling the global warming potential. So this is because the because the world average efficiencies are still much lower than the best available technologies available. So there is considerable reduction in GHG emissions by application of CO2 capture. However, the life cycle reduction rates are significantly lower than the CO2 capture rates at the power plant. So different CCS systems reduces life cycle GHG emissions by 74 to 78% for coal power plants and 64 to 73% for natural gas power plants. So direct emissions of CO2 at power plant without capture contribute to more than 90% of life cycle GHG emissions in coal and about 80% in case of natural gas. So the remaining CO2 equivalents in CCS chain are mainly emitted in the fuel supply chain dominated by coal mining for coal systems and gas production and transportation for natural gas systems. So we see that post-combustion capture systems also offer some benefit on acidification and particulate matter related impact categories as it co-captures SOx and NOx, so it offers these benefits as well. And we see that there is a typical increase in other impacts, environmental impacts, for example, in the toxicity related with the CCS systems. I'm not going into detail with this because I want to showcase the endpoint reflections of impact assessments. Different environment. So far with the environmental impact assessment, we could generate a comparison of different technologies on different environmental categories. But to make a decision, we need to get a more comparable understanding, which is easily understandable. And here comes the endpoint indicators, just showcasing one of the indicators, which is human health damage. So different environmental impacts are translated to the endpoint indicator. For example, climate change would contribute to certain human health damage. Particulate matters would contribute to human health damage. So different kind of midpoint indicators are translated to human health, to this endpoint indicator of human health damage in this figure. And it shows that the CCS variance significantly reduces the human health damage, which is measured in terms of disability adjusted life year loss. And with reduction of 67% for polarized coal, 71% for IDCC systems with capture, and 63% for natural gas systems with CCS. The reduction of human health damage by CCS is the result of the prevention of human health impact of climate change from conventional power plants. It is found that specific capture-related air emissions contribute less than 1% to toxicity-related human health damage. So there is a complete flow of evaluation techniques available for comparing different kind of CCS options, and for that matter, any kind of system. In conclusion of this comparison, I would just say that a comparative LCA of power generation systems with or without CCS shows that with CCS system have significant benefits in reduction of global warming potential, while CCS system offers advantage of reduced global warming potential. It has environmental trade-offs, primarily with eutrophication and toxicity impacts. In terms of endpoint damages, CCS systems offer clear advantage in significantly reducing human health damage from power generation. LCA of different CCS systems holistically identifies benefits and trade-offs and support informed decision for technology selection. I just wanted to briefly give you a glimpse that when this methodology is applied in this case to study different electricity generation technologies, including renewables, it shows that the renewable energy technologies have significantly lower pollution-related environmental impacts per unit of generation than the state-of-the-art coal-fired power plants in all considered impact categories. It also finds that wind and solar power plants tend to require more bulk materials in this case. Yeah. So all renewable technologies have significantly lower pollution-related environmental impacts. However, the wind and solar power plants require more bulk materials than coal and gas-based electricity generation. So these are material intensive. However, the environmental impacts of producing these bulk materials, which are needed by renewable technologies, is still small in absolute terms as compared to impacts from fuel production and combustion. High land use requirements are associated with hydropower reservoirs, coal mines, and solar power plants. Translating this into endpoint as human health and ecosystem quality measured as damage to measured as Dali's number and species year per kilowatt are here showing the normalized to per unit of electricity. It shows that for different electricity generation technologies, that renewable energy sources and nuclear have lower health impacts than coal or gas power. This advantage is mostly due to lower impacts from climate change, which tend to dominate health impacts from all technologies, including renewable energy. So this was an attempt to give you a glimpse of comparative environmental assessment methodology available and a glimpse of results that one could obtain. And as a way forward, as different electricity generation technologies may have different environmental impact trade-offs vis-a-vis GHG emissions or global warming potential, it is important to use LCA as a tool to holistically evaluate these comparative impacts, identify trade-offs, and guide technology selection. Thank you. I would like your comments or questions, if any.
Dear participants, if you have any question, please ask.
It could have been a lot of information, I think, in such a short span of time.
Dr. Bhavna, it's Priyanka here.
Yes, yes, Professor.
Since there aren't many questions,
Yes.
it's been a long day here toward the end of the day. So I must thank you. Thank you very much for taking time out, agreeing on such a short notice, and sharing the bird's eye perspective about the whole energy market from carbon neutrality and clean energy point of view. So thank you very much. And if there is any query, we will share it with you, and we will share the contact as well. Thank you very much.
Thank you very much.
We really look forward to
Thank you, ma'am.
collaborating some other time. Thank you. I see there is a hands up.
Okay, I'm still here.
Yeah. I have joined through my phone, so I can't see. Param, can you just see why somebody has raised the hand? Param, देखोगे? Chat में है या why he's raising his hand?
Yes, ma'am. I'm.
एक बार-
Vera, do you have any question? Please ask. In
You
chat,
have raised
there's
your
a
hand.
question.
Yeah.
Yes.
Yes, there is some question. I only realized that this is a day-long program, like course for the participants. So it's already like towards the end of the day. So I think it's good.
Toward the end of the day, toward the end of the course. We are concluding tomorrow. So
Okay. Okay.
Abera from Ethiopia, do you have any question? You want to ask something?
I think the mic is muted. So, or okay. And how we can calculate?
Yes, ma'am. There's a question in chat box.
How we read out
How we
further?
can calculate long-lasting materials? Long-lasting materials. Yes.
Long-lasting materials. LCA of long-lasting materials, I mean?
I assume so, yes.
Yeah. So there is already a consideration of lifetime involved whenever we take any LCA, even for these systems, or for example, for vehicles, we could take a lifetime of 10 years, for power plants for say 30 years. So there is always a consideration of the lifetime, without which, because then only we can allocate the material per functional unit. So there is always a consideration of lifetime depending on how long that system is going to last. So it is inherent to the LCA modeling. We can take this further if you want more details at how we could include it into inventory, because it is reflected in inventory modeling of any system. Okay. Okay, good. So I think, Professor Priyanka, that
Yes.
be all.
Yes. Thank you very much, Dr. Bhavna. Thank you very much. and
Thank you
really
very
lovely
much for
that-
having me. Thank you. Bye-bye.
Thank you. Have a good day. Bye-bye. So, hello, participants. We are done for the day today. See you tomorrow at 10 a.m. Please note,
Hello,
tomorrow at
hello.
10 a.m. India times.
Hello, Ma. Hello, Ma.
Yes. Yes.
Please, I have one observation. Please, when are we going to get the materials and the
Oh, we will upload. Yes, we will upload almost all of them. Some of them didn't give consent to share their material online, but majority of them have given. We will upload it very soon on our probably on YouTube, and we will share the link with you.
Okay, thank you so much, ma.
Yeah, thank you. See you tomorrow at 10 a.m. Take care.
All right.
Bye-bye. Take care. Bye-bye.
Professor, is still there?
Yes.
Just a quick one. I think you're about to say that tomorrow is the last day.
Yes.
Any chance you've factored in a post-mortem review of the session?
Yes, we will do it. So, sorry, come again. What did you say?
Post-review of the session. Any chance we've factored in a session to post-review?
So, what do you propose in that?
I'm asking if if the program has factored a session to review the entire session, both from a delivery side, which is your side, and recipient side, which is our side.
So you are saying if you can view it again later?
No. Post-mortem review.
Oh, I have to, because I don't understand what exactly you are asking, but let me tell you what we are going to do tomorrow. Tomorrow morning, there will be 2 sessions. Two of the speakers will come and speak. And then there is a lunch break. And after the lunch break, normally what we resume at 2 p.m. India time. So we'll come back at 2 p.m. India time. We will have an interaction. We will take your feedback, listen from you.
Exactly.
Yeah, we will be doing that. Yes, we will be doing it tomorrow at 2 p.m. India times. Yes. So morning session, we will have two talks. Evening time, we will be doing interaction with you. Yes.
Awesome.
Yeah.
All right. See you tomorrow. Thank you for that feedback.
Yeah. See you tomorrow. Thank you. See you tomorrow.
Dear participants, we have announcement. We will send a feedback form on your mail, so you can just fill the form. Okay. Thank you for joining us today.